Listening practice. Forward. The management of solid waste stands as one of the most pressing challenges of the 21st century. As urbanization accelerates, populations grow, and consumption patterns intensify, the volume and complexity of waste generated globally have reached unprecedented levels. Traditional methods of disposal, landfilling, incineration, and indiscriminate dumping are no longer viable in a world grappling with climate change, resource depletion, and environmental degradation. Advanced solid waste management, innovations for a sustainable future emerges at a critical juncture, offering a roadmap to transform waste from a liability into a resource while safeguarding ecosystems and human health. This book underscores the urgency of adopting innovative, circular, and technology-driven approaches to solid waste management. From mitigating greenhouse gas emissions linked to landfills to addressing the scourge of plastic pollution in oceans, the solutions explored here are not merely technical but deeply interconnected with policy, economics, and societal behavior. By bridging the gap between cutting-edge research and practical implementation, this work aims to inspire policymakers, engineers, entrepreneurs, and communities to reimagine waste as a cornerstone of sustainable development. The path forward demands collaboration, creativity, and courage. Let this book serve as both a guide and a catalyst for action in the global pursuit of a zero-waste future. Preface. Purpose. This book is designed to address the multifaceted challenges of modern solid waste management through a lens of innovation and sustainability. It synthesizes decades of research, technological advancements, and real-world case studies to present actionable strategies for reducing waste generation, enhancing resource recovery, and minimizing environmental harm. Scope. The scope of this work spans the entire life cycle of solid waste from generation and collection to treatment, recycling, and final disposal. It explores both municipal and industrial waste streams, with a focus on emerging contaminants, e.g., microplastics, e-waste, and novel technologies, e.g., AI-driven sorting, plasma gasification. Special emphasis is placed on the circular economy paradigm, which redefines waste as a valuable resource to be reintegrated into production cycles. Audience. This book is intended for a diverse audience, environmental engineers and scientists seeking advanced technical insights, urban planners and policymakers crafting waste management regulations and infrastructure, sustainability professionals and entrepreneurs developing circular business models, academics and students in environmental studies, engineering, and public policy, community leaders and advocates driving grassroots waste reduction initiatives. Structure. The book is organized into 7 thematic parts, each building on the previous to provide a holistic understanding of advanced solid waste management. Part I establishes foundational concepts, while subsequent sections delve into waste assessment, circular strategies, cutting-edge technologies, digital innovations, socio-economic dimensions, and future challenges. Case studies and practical examples are interwoven to illustrate global successes and lessons learned. Acknowledgements. We extend gratitude to the researchers, industry experts, and policymakers whose contributions shaped this work. Special thanks to the communities worldwide pioneering zero-waste practices. Their resilience and ingenuity remind us that a sustainable future is not only possible but already in motion. This forward and preface set the stage for the book, emphasizing urgency, innovation, and collaboration while clarifying its goals and relevance to readers. Let me know if you'd like to expand on specific sections. Part I, Fundamentals of Solid Waste Management 1. Introduction to Solid Waste 1.1 Definitions, Municipal, Industrial, Hazardous, and Electronic Waste. Solid waste encompasses a broad spectrum of discarded materials, categorized by source and composition. Municipal solid waste, MSW. Everyday items from households, commercial establishments, and institutions, e.g., food scraps, packaging, textiles. Industrial waste, byproducts of manufacturing, construction, and mining, e.g., slag, scrap metal, chemical residues. Hazardous waste, toxic, flammable, corrosive, or reactive materials requiring specialized handling, e.g., batteries, pesticides. Medical waste, Electronic waste, e-waste discarded electronics containing recoverable metals and hazardous components, e.g., smartphones, laptops, circuit boards. Key challenges, overlap between categories, e.g., e-waste often contains hazardous materials. Lack of standardized global definitions complicating cross-border regulation. 1.2 Global waste generation trends and drivers, current statistics. The World Bank estimates global annual waste generation at 2.24 billion metric tons, 2023, projected to rise to 3.88 billion tons by 2050 under business as usual scenarios. Regional disparities, high-income countries generate 34% of global waste but account for only 16% of the population. Low-income nations often lack infrastructure to manage rapidly growing waste volumes. Key drivers, urbanization, over 55% of the global population resides in cities, where per capita waste generation is 2-3 times higher than rural areas. Consumerism, fast fashion, single-use plastics, and planned obsolescence fuel waste growth. Policy gaps, weak enforcement of extended producer responsibility, EPR, and recycling mandates. Emerging trends, surges in pandemic-related waste, e.g., PPE, packaging from e-commerce. Rising e-waste linked to digitalization, e.g., 53.6 million metric tons generated globally in 2023. 1.3 The life cycle of solid waste, from generation to disposal. The life cycle framework maps the journey of waste from creation to final fate. 1 Generation, waste originates from households, industries, agriculture, and institutions. 2 Collection, efficiency varies widely from formal municipal systems to informal sector in developing economies. 3 Transportation, emissions from fossil fuel-dependent waste trucks remain a sustainability challenge. 4 Processing/treatment, material recovery, sorting recyclables, e.g., metals, plastics. Biological treatment, composting organic waste. Thermal treatment, incineration with energy recovery. 5 Disposal, landfilling, dominates globally but contributes to methane emissions and groundwater contamination. Open dumping, still prevalent in regions lacking infrastructure, posing severe health risks. Critical issues in the life cycle, linear versus circular systems. Traditional take-make-dispose models contrast with circular approaches prioritizing reuse and recycling. Informal sector role, in many countries, informal workers handle 50–80% of recycling, often under hazardous conditions. Leakage, up to 30% of plastic waste escapes formal systems, polluting oceans and ecosystems. Key takeaways for Chapter 1. Solid waste is not a monolithic challenge, its diversity demands tailored solutions. Global disparities in waste generation and management highlight the need for equitable, context-specific strategies. Transitioning from linear disposal to circular resource recovery is central to sustainable waste management. This chapter lays the groundwork for understanding the scale, complexity, and interconnectedness of solid waste systems, a foundation essential for exploring advanced solutions in subsequent sections. Would you like to refine or expand any subsection further? Part I, Fundamentals of Solid Waste Management 2. Environmental and Public Health Impacts. 2.1 Landfill emissions and leachate contamination. Landfills are among the largest anthropogenic sources of methane, CH, a greenhouse gas 28–36 times more potent than CO over a century. Key issues include, emissions, methane accounts for 12% of global CH emissions, accelerating climate change. CO and volatile organic compounds, VOX, from decomposing organic waste. Leachate, toxic liquid formed by rainwater percolating through waste, carrying heavy metals, e.g., lead, arsenic, pharmaceuticals, and chlorinated compounds. Contaminates groundwater and surface water, threatening drinking supplies and aquatic ecosystems. Public health risks, chronic exposure linked to cancers, respiratory diseases, and developmental disorders in nearby communities. Example, the Gazipur landfill in Delhi, India, emits 2.7 million cubic meters of methane daily while contaminating the Yamuna River. Mitigation strategies: landfill gas capture systems for energy generation. Liners and leachate treatment plants, e.g., reverse osmosis, activated carbon filtration. 2.2 Air pollution from incineration and open burning. Controlled incineration releases dioxins, furans, and particulate matter, PM, even in modern facilities with scrubbers. Heavy metals, e.g., mercury from electronics, accumulate in fly ash, requiring secure disposal. Waste to energy, WTE, trade-off: while reducing landfill reliance, incinerators in the EU emit 1 ton of CO per ton of waste burned. Open burning, common in low resource settings, contributing to 10% of global black carbon emissions. Releases carcinogens like benzene and polycyclic aromatic hydrocarbons, PAHs. Health impact, linked to 7 million premature deaths annually, from air pollution, disproportionately affecting informal waste workers. Case study: in Southeast Asia, seasonal agricultural burning and plastic waste combustion create transboundary haze, exacerbating respiratory illnesses across Malaysia and Singapore. 2.3 Microplastics, toxins, and long-term ecological damage. Microplastics, 5 mm, enter ecosystems via degraded plastic waste, wastewater, and tire abrasion. Found in 83% of global tap water and 90% of bottled water, orb media. Marine impact, ingested by plankton to whales, disrupting endocrine systems and food webs. Persistent toxins, PFAS, forever chemicals, from packaging and firefighting foams accumulate in soil and water, resisting degradation for millennia. Heavy metals, lead from batteries and cadmium from electronics bioaccumulate in crops, entering human diets. Ecological tipping points: soil microbiome disruption reduces agricultural productivity. Coral reef mortality from plastic suffocation and chemical leaching. Emerging threats: nanoplastics, less than or equal to 100 nm, penetrating cellular barriers in organisms. Antibiotic resistance genes, ARGs, spread via landfill leachate into water systems. Key takeaways for Chapter 2: landfills and incineration are double-edged swords, offering waste reduction but posing significant climate and health risks. Microplastics and toxins represent a slow-motion crisis with irreversible ecological consequences. Vulnerable populations, informal workers, low-income communities, and coastal regions bear the heaviest burden. This chapter underscores the urgent need to transition from waste disposal to prevention and circularity, themes explored in later sections. Let me know if you'd like to dive deeper into specific pollutants or case studies. Part I: Fundamentals of Solid Waste Management 3. Policy and Regulatory Landscape. 3.1 International Agreements, Basel Convention, SDGs, Paris Accord, Basel Convention, 1989, Purpose: regulates transboundary movements of hazardous waste to prevent dumping in developing nations. Relevance: addresses e-waste and plastic waste trafficking, with the 2019 amendment tightening restrictions on exporting unsorted plastics. Impact: reduced illegal dumping but challenges persist due to weak enforcement in some regions. Sustainable Development Goals, SDGs, SDG 12, Responsible Consumption and Production, Target 12.4, Environmentally Sound Management of Chemicals and Waste. Target 12.5, Substantially reduce waste generation through recycling and reuse by 2030. SDG 11, Sustainable Cities promotes municipal waste management improvements. Paris Agreement, 2015, linked to waste. Methane from landfills accounts for 3% of global GHG emissions. Waste to energy and landfill gas capture align with climate goals. National contributions. NDCs. Over 70 countries include waste sector strategies in their climate pledges. 3.2 National Waste Management Policies and Circular Economy Laws, European Union, Circular Economy Action Plan, 2020 mandates 55% municipal waste recycling by 2025 and bans single-use plastics, e.g., cutlery, straws. Waste Framework Directive, sets hierarchy, prevention, reuse, recycle, recover, dispose. Japan, Sound Material Cycle Society, achieved 20% reduction in waste generation, 2020, via strict recycling laws and industrial symbiosis. Developing Economies, India, Swachh Bharat Mission, 2014, improved urban waste collection but struggles with informal sector integration. Rwanda, pioneered plastic bag bans, 2008, and promotes upcycling enterprises. Challenges, funding gaps, lack of infrastructure, and political will hinder policy execution in low-income nations. 3.3 Extended Producer Responsibility, EPR, and Compliance Strategies, EPR Frameworks, EU WEEE Directive, requires electronics producers to fund collection/recycling, e.g., 65% e-waste recovery target by 2025. Packaging laws, Germany's dual system, Green Dot, shifts recycling costs to manufacturers. Compliance mechanisms, financial instruments, deposit return schemes, e.g., Norway's 97% plastic bottle return rate. Penalties, South Korea's volume-based waste fees reduced household waste by 18%, 2013-2020. Certification, Cradle to Cradle, C2C, certification incentivizes sustainable product design. Challenges, free rider problem, non-compliant firms undermine sector-wide progress. Complexity, multi-stakeholder coordination, producers, municipalities, recyclers, slows implementation. Key takeaways for Chapter 3, international agreements provide a global framework, but national/local adaptation determines success. Circular economy laws drive innovation, e.g., EU's eco-design standards, while EPR shifts accountability to producers. Equity gaps persist, developing nations need funding and tech transfers to meet waste management targets. This chapter illustrates how policy shapes waste systems from curbing pollution to fostering circularity and underscores the need for inclusive, enforceable regulations. Let me know if you'd like to explore specific country case studies or policy instruments in more detail. Part 2, Waste Characterization and Assessment 4. Waste Auditing and Composition Analysis 4.1 Sampling Techniques for Heterogeneous Waste Streams. Accurate sampling is critical for understanding waste composition, which varies widely by source, season, and region. Key methods include, stratified random sampling, divides waste streams into subgroups, e.g., residential, commercial, for targeted analysis. Quartering, reduces bulk waste into manageable portions while preserving representativeness. Grab sampling, manual collection at specific intervals, often used for small-scale audits. Mechanical sorting, automated conveyor belts with sensors to segregate materials, e.g., metals, plastics. Challenges, heterogeneity, organic waste degradation alters composition over time. Safety risks, hazardous materials, e.g., sharps, chemicals, require protective gear. Bias, informal settlements may be underrepresented in municipal audits. Case study, the New York City Waste Characterization Study, 2023, used stratified sampling across 50 neighborhoods to reveal 34% organic waste in residential streams, prompting expanded composting programs. 4.2 Data-driven waste characterization tools. Modern technologies enhance precision and scalability in waste analysis. AI and machine learning, image recognition, cameras and algorithms classify waste in real time, e.g., GRIPARIT's AI-powered waste analytics. Predictive modeling, forecasts waste generation trends using demographic and economic data. Spectral analysis, near-infrared, NIR, spectroscopy, identifies polymer types in plastic waste streams. X-ray fluorescence, XRF detects heavy metals in e-waste. IoT-enabled sensors, smart bins track fill levels and composition, optimizing collection routes. Impact, recycling contamination reduction. Denver's AI-driven sorting system cut plastic contamination by 22%, 2022. Cost savings, waste audits using digital tools lower labor expenses by 30-50%. 4.3 Risk assessment of hazardous and medical wastes. Risk assessment frameworks prioritize threats to human health and ecosystems. 1. Hazard identification, chemical toxicity, testing for carcinogens, e.g., asbestos, dioxins. Biological hazards, pathogens in medical waste, e.g., hepatitis B, SARS-CoV-2. 2. Exposure assessment, pathways, inhalation, incinerator emissions, ingestion, contaminated water, or dermal contact, landfill workers. 3. Risk characterization, quantifies likelihood of harm using tools like the EPA's IRIS database. Medical waste case study, during the COVID-19 pandemic, 6 million tons/day of medical waste, syringes, masks, overwhelmed incineration capacity in India, triggering open dumping and antibiotic resistance risks. Regulatory tools, hazard ranking system, HRS scores sites for Superfund cleanup, USA. Biomedical waste rules, India mandates autoclaving and shredding of infectious waste. Emerging risks, nanoparticles from electronic waste penetrating biological membranes. Pharmaceutical waste, hormones and antibiotics disrupting aquatic ecosystems. Key takeaways for Chapter 4, Accurate waste characterization requires blending traditional sampling with advanced technologies like AI and spectroscopy. Data-driven tools enable dynamic, cost-effective decision-making for municipalities and industries. Hazardous and medical waste risks demand localized frameworks to address unique environmental and health vulnerabilities. This chapter equips readers with methodologies to quantify and mitigate waste-related risks, a foundation for designing remediation and circular economy strategies in later sections. Would you like to explore specific tools, e.g., LCA software or regional case studies in more depth? Part 2, Waste Characterization and Assessment 5. Advanced Analytical Methods 5.1 Spectroscopy and chromatography for contaminant detection. Advanced analytical techniques are critical for identifying and quantifying pollutants in waste streams. Spectroscopy, inductively coupled plasma mass spectrometry, ICP-MS detects trace heavy metals, e.g., lead, cadmium, in landfill leachate with parts per trillion precision. Fourier transform infrared, FTIR, spectroscopy, identifies polymer types in microplastics from wastewater sludge. UV-vis spectroscopy, monitors organic pollutants like dyes and pharmaceuticals in industrial effluent. Chromatography, gas chromatography mass spectrometry, GCMS analyzes volatile organic compounds, VOX, emitted from incinerators, such as benzene and toluene. High-performance liquid chromatography, HPLC quantifies endocrine-disrupting chemicals, e.g., bisphenol A, in recycled plastics. Case study, in California's Salton Sea, GCMS revealed perchlorate contamination from agricultural runoff, prompting remediation of irrigation drainage systems. Challenges, high equipment costs and specialized training requirements. Complex waste matrices, e.g., mixed plastics, complicating analysis. 5.2 AI-powered waste sorting and classification systems. Artificial intelligence revolutionizes waste segregation, enhancing efficiency and accuracy. Computer vision, AMP Robotics Neuron trademark platform, uses neural networks to identify and sort 80+ material types at 160 picks per minute, achieving 99% purity in recycling streams. Zen Robotics Heavy Picker, deploys deep learning to recover construction waste, e.g., wood, metals, with 95% accuracy. Robotics integration, waste-specific data sets, AI models trained on millions of waste images to distinguish between PET, HDPE, and multi-layer packaging. Real-time analytics, sensors on conveyor belts adjust sorting protocols based on waste composition fluctuations. Impact, contamination reduction, a UK facility reduced plastic recycling contamination by 30% using AI-guided systems. Labor savings, automated sorting cuts manual labor costs by 50% in material recovery facilities, MRFs. Challenges, high upfront investment and energy consumption. Limited adaptability to novel or degraded materials. 5.3 Life Cycle Assessment, LCA, of Waste Management Practices. LCA quantifies environmental impacts across a product's life cycle, guiding sustainable decision-making. Methodology, 1 Goal and scope, define system boundaries, e.g., cradle-to-grave versus cradle-to-gate. 2 Inventory analysis, collect data on energy use, emissions, and resource inputs. 3 Impact assessment, evaluate effects on climate change, eutrophication, and human health. 4 Interpretation, identify hotspots and improvement opportunities. Key findings, landfilling versus incineration. WTE incineration reduces landfill methane but emits more CO per ton. Recycling aluminum, saves 95% energy compared to virgin production, but collection inefficiencies offset gains. Bioplastics, compostable PLA has lower carbon footprint than PET but requires industrial composting to degrade. Software tools, CIMAPro and OpenLCA, model complex waste scenarios and compare circular strategies. EcoInvent database, provides life cycle inventory data for 18,000 plus processes. Case study, an LCA of Denmark's circular textile initiative showed that recycling cotton reduced water use by 70% but highlighted challenges in dye removal. Key takeaways for Chapter 5, Spectroscopy and chromatography enable precise contaminant tracking, vital for regulatory compliance and remediation. AI-driven sorting bridges the gap between waste volume and recycling capacity, though scalability depends on cost and infrastructure. LCA reveals trade-offs in waste strategies, emphasizing the need for context-specific solutions, e.g., biogas versus composting for organics. This chapter underscores how advanced analytics and AI are transforming waste management from reactive disposal to proactive resource recovery, a cornerstone of the circular economy. Let me know if you'd like to explore specific technologies, e.g., hyperspectral imaging, or LCA case studies in greater detail. Part 3, Waste Minimization and Circular Economy. 6. Source Reduction and Sustainable Design. 6.1 Eco-Design Principles for Waste Prevention. Eco-design integrates environmental considerations into product development to minimize waste at the source. Key principles include, dematerialization, reducing material use without compromising function, e.g., lightweight packaging, digital alternatives to physical goods. Modularity and repairability, designing products for disassembly and longevity, e.g., Fairphone's modular smartphones. Material substitution, replacing virgin plastics with bio-based or recycled materials, e.g., Adidas Futurecraft. Loop sneakers made from 100% recyclable TPU. Toxicity reduction, eliminating hazardous additives, e.g., phthalates in PVC, PFAS in textiles. Case studies, IKEA's Circular Design Framework aims for 100% renewable/recycled materials by 2030, with products like the Kungsbacka kitchen fronts made from recycled wood and PET bottles. Cradle to Cradle, C2C, certification, guides brands like Method and Steelcase in creating closed-loop products. Challenges, higher upfront costs for sustainable materials. Lack of standardized eco-design regulations globally. 6.2 Industrial Ecology and Zero Waste Manufacturing. Industrial ecology fosters symbiotic systems where waste from one process becomes input for another. Industrial symbiosis, Kalundborg symbiosis, Denmark. A network where a power plant's waste heat warms fish farms, and gypsum byproducts from desulfurization are used in construction. Zero waste manufacturing, Toyota's Comigo plant achieved 99% waste diversion by repurposing metal shavings into cement and sludge into bricks. TerraCycle's Loop initiative partners with brands to deliver products in reusable containers, collected and refilled post-use. Circular Metrics, Zero Waste to Landfill, ZWTL certification pursued by companies like Subaru and GM, Material Circularity Indicator, MCI developed by the Ellen MacArthur Foundation to quantify circularity. Challenges, high capital costs for retrofitting factories. Geographic clustering required for symbiotic networks. 6.3 Consumer behavior and demand-side strategies. Shifting consumption patterns is critical to waste minimization, nudging strategies, deposit return schemes, DRS. Norway's 97% plastic bottle return rate via financial incentives. Eco-labeling, EU energy label and how to recycle logos guide sustainable choices. Education campaigns, Japan's Matena movement, cultural emphasis on no waste through school programs and community workshops. RAP's Love Food Hate Waste reduced UK household food waste by 21%, 2007-2018. Collaborative consumption, Patagonia's Worn Wear, resells refurbished clothing, extending garment life cycles. Tool libraries and sharing platforms, reduce ownership of rarely used items. Behavioral barriers, convenience culture, single-use plastics thrive due to low-cost, on-the-go lifestyles. Greenwashing, misleading claims, e.g., biodegradable plastics requiring industrial composting, erode trust. Emerging tools, digital product passports, DPPs provide transparency on materials and recyclability via QR codes, EU mandate by 2030. Gamification, apps like Olio reward users for redistributing surplus food. Key takeaways for Chapter 6, Eco-design reimagines products as regenerative resources, reducing reliance on landfills and virgin materials. Industrial symbiosis and zero-waste manufacturing demonstrate that cross-sector collaboration can turn waste into wealth. Consumer engagement requires a mix of incentives, education, and systemic shifts to overcome entrenched habits. This chapter bridges technical innovation with human-centric strategies, illustrating how waste minimization hinges on rethinking design, production, and consumption in tandem. Let me know if you'd like to explore specific policies, e.g., plastic taxes or behavioral science models in more detail. Part 3, Waste Minimization and Circular Economy 7. Recycling and Resource Recovery 7.1 Advanced Material Recovery Facilities, MRFs. Advanced MRFs integrate cutting-edge technologies to enhance sorting efficiency and material purity. Key technologies, AI and robotics. AMP robotics AI-guided systems achieve 99% purity in sorting plastics and metals. Optical sorters use near-infrared, NIR, spectroscopy to identify material types at high speeds. Eddy current separators recover non-ferrous metals like aluminum from mixed waste streams. Benefits, increased recycling rates, e.g., San Francisco's Recology facility processes 500-600 tons/day with 80% diversion. Reduced contamination, enabling higher value recycled materials. Challenges, high capital costs, $10–20 million for facility upgrades. Requires skilled technicians for maintenance and operation. Global examples, UK's Veolia Southwark MRF, processes 135,000 tons/year using AI and robotics. Singapore's Semeco landfill MRF, prioritizes resource recovery in a land-scarce nation. 7.2 Chemical recycling of plastics and composites. Chemical recycling breaks down plastics into molecular components for reuse, addressing limitations of mechanical recycling, processes, pyrolysis, heats plastics to 400–800 degrees C in oxygen-free environments, producing pyrolysis oil, used by Agilex to recycle polystyrene. Depolymerization, reverts polymers to monomers, e.g., Carbio's enzymatic recycling of PET. Gasification, converts plastics to syngas for chemical production, e.g., Enercom's Montreal facility. Advantages: handles mixed, multilayered, or contaminated plastics, e.g., food packaging. Produces virgin quality materials, supporting closed-loop systems. Challenges: high energy consumption and CO emissions, e.g., pyrolysis emits 1.53 ton CO/ton plastic. Limited scalability due to technical and regulatory hurdles. Case study: Loop Industries' Infinite Loop trademark, partners with L'Oréal and PepsiCo to produce 100% recycled PET bottles. 7.3 Bio-based materials and closed-loop systems. Bio-based materials derived from renewable resources align with circular economy principles. Materials and applications: polylactic acid, PLA, compostable bioplastic from cornstarch, used in packaging, e.g., NatureWorks Injo trademark, mycelium, mushroom-based materials for insulation and packaging, e.g., Ecovative design, algae-based polymers, used in textiles and biodegradable films, e.g., AlgaeNet, closed-loop integration. Composting infrastructure, required for PLA breakdown, e.g., San Francisco's citywide composting program. Chemical recycling compatibility: some bioplastics can be depolymerized alongside traditional plastics. Challenges: contamination risks, PLA in PET recycling streams reduces recyclate quality. Land use: scaling bio-based feedstocks competes with food production, e.g., corn for PLA. Innovations: FA, polyhydroxyecanotes, marine degradable bioplastics from bacterial fermentation, e.g., Danimer Scientific. Digital watermarks: Holy Grail 2.0 initiative uses invisible codes to improve sorting of bio-based packaging. Key takeaways for Chapter 7, Advanced MRFs leverage AI and robotics to transform recycling economics, though upfront costs remain a barrier. Chemical recycling complements mechanical methods but requires policy support to scale sustainably. Bio-based materials offer renewable alternatives but demand robust composting and sorting systems to avoid ecosystem harm. This chapter highlights the synergy between technological innovation and systemic design in achieving circularity, emphasizing the need for cross-sector collaboration and consumer education. Let me know if you'd like to explore specific technologies, e.g., enzymatic recycling, or regional policies, e.g., EU Single-Use Plastics Directive, further. Part 3, Waste Minimization and Circular Economy 8. Circular Economy Frameworks 8.1 Urban Mining and E-Waste Valorization Definition: Urban mining extracts valuable materials from discarded electronics, e-waste, and industrial waste streams. Key processes: mechanical processing, shredding and separating metals, e.g., gold, copper, from circuit boards. Hydrometallurgy, using chemical solutions to leach rare earth elements, e.g., neodymium from hard drives. Pyrolysis, recovering carbon black from tires for reuse in rubber products. Global impact: only 17.4% of 53.6 million tons of e-waste, 2023, is formally recycled, Global E-Waste Monitor. Urban mining could supply 40% of global copper demand by 2040, World Bank. Case studies: Bamako, Belgium recovers 17 plus precious metals from e-waste, achieving 95% purity. Japan's ecotowns integrate urban mining into municipal waste systems, targeting 100% e-waste recycling by 2030. Challenges: toxic substances, e.g., mercury, lead, require safe handling. Informal recycling in developing nations poses health risks, e.g., Agbogbloshie, Ghana. 8.2 Food waste to energy and biogas systems process overview, converts organic waste into renewable energy via anaerobic digestion, AT, or thermal treatment. Anaerobic digestion, biogas output, 60–70% methane, used for electricity, heat, or vehicle fuel, e.g., CNG. Digstate, nutrient-rich byproduct for agricultural fertilizer. Thermal valorization, incineration with energy recovery, generates 500-600 kWh per ton of waste. Global examples: Oslo, Norway, powers 150 city buses with biogas from food and sewage waste. San Francisco's Zero Waste program diverts 80% of organic waste to AD facilities. Challenges: contamination, e.g., plastics in food waste, reduces biogas yield. High capital costs for AD infrastructure, $2 to $5 million for small-scale plants. Innovations: AI-optimized digesters, adjust feedstock mixes in real time, e.g., BioBang registered trademark. Decentralized systems, small-scale digesters for rural communities, e.g., home biogas. 8.3 Industrial symbiosis networks definition: collaborative networks where industries exchange byproducts, energy, or resources. Principles: waste as resource, cement plants using fly ash from power plants. Energy cascading, excess heat from factories warming nearby greenhouses. Case studies: Kalundborg symbiosis, Denmark, 20+ partnerships save 635,000 tons of CO/year. A power plant's surplus steam heats 5,000 local homes. Kwinana Industrial Area, Australia, CO from hydrogen production captured for urea fertilizer manufacturing. Benefits: cost savings, Kalundborg's network reduces annual expenses by $24 million. Resource efficiency, 90% waste diversion in symbiotic clusters. Challenges: geographic proximity required for material exchange. Regulatory barriers, e.g., waste classification laws. Future trends: digital platforms, match waste suppliers with users, e.g., SYNERGIE registered trademark. Policy incentives, tax breaks for cross-industry resource sharing, e.g., EU's circular economy package. Key takeaways for Chapter 8, Urban mining transforms e-waste into strategic reserves of critical minerals, reducing reliance on virgin mining. Food waste to energy bridges waste management and renewable energy goals but requires contamination control. Industrial symbiosis exemplifies circularity in action, turning waste into economic and environmental assets. This chapter illustrates how circular frameworks blend innovation, collaboration, and policy to redefine waste as a resource critical for achieving global sustainability targets. Let me know if you'd like to explore metrics, e.g., circularity indicators or regional policy models further. Part 4, Advanced Treatment Technologies 9. Thermal Treatment Innovations 9.1 Plasma Gasification and Pyrolysis Definition. Plasma gasification uses ionized gas, plasma, at temperatures exceeding 7,000 degrees Celsius to convert organic waste into syngas, a mix of CO, H, and inorganic waste into inert slag. Pyrolysis thermally decomposes waste at 300-800 degrees C in oxygen-free conditions, yielding bio-oil, char, and syngas. Key processes: plasma torches generate extreme heat to break molecular bonds, e.g., Alterna's Westinghouse plasma systems. Feedstock flexibility handles municipal solid waste, MSW, medical waste, and hazardous materials. Outputs: syngas for electricity/heat, slag for construction materials, e.g., roads. Benefits: emissions reduction, 95% lower dioxins versus incineration. Landfill diversion, processes non-recyclable waste. Challenges: high costs, $500 $700/ton processing versus $100/ton for landfilling. Energy intensity, requires 0.81.2 mWh/ton of waste. Case study: Yotashina, Japan, world's largest plasma gasification plant processes 300 tons/day of MSW, powering 30,000 homes. 9.2 Waste to energy, WTE, with carbon capture definition, integrates carbon capture, utilization, and storage, CCUS, with WTE incineration to mitigate CO emissions. Key technologies: post-combustion capture, amine scrubbers capture CO from flue gas, e.g., CRI's CanSolve registered trademark. Oxy-fuel combustion, burns waste in pure oxygen, simplifying CO separation. Benefits: emissions reduction, captures 90% plus of CO, e.g., Oslo's Kulmetsrud WTE aims for full CCS by 2030. Circular synergy, CO used in cement production or algae cultivation. Challenges: costs, adds $50 100/ton to WTE operations. Energy penalty, 15-25% plant efficiency loss. Case study: Norway's Longship project, pilots CCUS at WTE plants to store CO under the North Sea. 9.3 Hybrid incineration systems for hazardous waste definition, combines thermal treatments, e.g., plasma, rotary kilns, to optimize hazardous waste destruction. Key features: rotary kill and plasma, kills pre-treat waste, plasma finishes toxics, e.g., polychlorinated biphenyls. Catalytic oxidation, destroys volatile organic compounds, VOX, at lower temperatures. Benefits: efficiency, achieves 99.99% destruction of persistent organic pollutants, POPs. Versatility, treats chemicals, pharmaceuticals, and asbestos. Challenges: complexity, requires advanced control systems. Regulatory hurdles, strict permits for handling PCBs and dioxins. Case study: Veolia's Swansea plant, UK hybrid system processes 100,000 tons/year of hazardous waste, including radioactive materials. Key takeaways for Chapter 9, Plasma gasification offers high-temperature precision for diverse wastes but faces scalability challenges. WTE with CCUS bridges energy recovery and climate goals, dependent on policy incentives. Hybrid systems enhance safety for hazardous waste but demand technical expertise. This chapter highlights cutting-edge thermal technologies reshaping waste into energy and materials, underscoring innovation's role in balancing efficiency, cost, and sustainability. Let me know if you'd like to explore specific technical workflows, e.g., gasifier designs or regional policy drivers. Part 4, Advanced Treatment Technologies 10. Biological treatment methods 10.1 Aerobic and anaerobic digestion optimization. Aerobic digestion process uses oxygen and microorganisms, e.g., Bacillus, Pseudomonas, to break down organic waste into CO, water, and compost. Optimization strategies: temperature control, maintain 55-60 degrees C for thermophilic digestion, faster degradation. Aeration management, smart sensors adjust oxygen levels to prevent over/under aeration. CO digestion, mixing food waste with agricultural residues, e.g., manure, balances C/N ratios. Anaerobic digestion, AD, process, microbes decompose organic matter in oxygen-free environments, producing biogas, CHNCO, and digestate. Optimization tactics, inoculum enrichment, adding specialized consortia, e.g., methanocida, boosts methane yield. Two-stage systems, separate hydrolysis/acidogenesis from methanogenesis to enhance efficiency. Pretreatment, ultrasonic or thermal hydrolysis breaks down lignocellulosic waste, e.g., crop residues. Case studies: Milwaukee's Jones Island plant, processes 300,000 tons/year of biosolids via AD, generating 8 MW of electricity. Singapore's Twas Nexus, integrates AD with incineration, achieving 90% energy self-sufficiency. Challenges: foaming and ammonia inhibition in AD. High energy input for aerobic systems in large-scale operations. 10.2 Bioleaching for metal recovery definition, uses acidophilic bacteria, e.g., Acidithiobacillus ferruxidans, to oxidize metals from ores, e-waste, or industrial sludge. Process steps: 1. Microbial colonization: bacteria adhere to metal surfaces, secreting sulfuric acid and Fe3 ions. 2. Leaching: metals dissolve into solution, e.g., Cu2, O. 3. Recovery: electrowinning or precipitation extracts metals from leachate. Applications: e-waste recycling, recovers gold, 95% efficiency, and copper from circuit boards. Mining waste, treats tailings to extract residual metals, e.g., zinc, nickel. Advantages: low energy versus smelting, cuts CO by 50%, processes low-grade ores uneconomical for traditional methods. Challenges: slow kinetics, weeks to months. Acidic runoff risks requiring neutralization. Case study: Biosigma, Chile uses biolayacking to extract copper from low-grade ores, producing 180,000 tons/year with 30% cost savings. 10.3 Fungal and enzymatic degradation of complex wastes. Fungal degradation: white rot fungi, e.g., Phanerochaete chrysosporium, produce lignin peroxidase and manganese peroxidase to break down lignin in agricultural waste. Applications: textile waste, degrade synthetic dyes in wastewater. Plastics: Aspergillus tubangensis breaks down polyurethane in weeks. Enzymatic degradation: key enzymes, PETase, engineered enzymes, e.g., phosphatase from UT Austin, hydrolyze PET plastics into monomers at 50 degrees Celsius. Lipases: degrade fats/oils in food waste. Innovations: immobilized enzymes, attached to nanoparticles or membranes for reuse, e.g., Novozymes Everlase. CRISPR-enhanced strains, fungi modified to overproduce lignocellulolytic enzymes. Case studies: Pestalotiopsis microspora, a rainforest fungus, degrades polyurethane in anaerobic landfills. Carbios, France, industrial-scale enzymatic recycling of PET achieves 97% depolymerization in 10 hours. Challenges: enzyme stability under industrial conditions, pH, temperature. High production costs for tailored microbial consortia. Key takeaways for Chapter 10, Aerobic/anaerobic digestion optimization maximizes energy recovery and compost quality, critical for urban organic waste. Biolayacking offers a sustainable alternative to metal extraction but requires robust containment to prevent acid pollution. Fungal/enzymatic systems target complex pollutants, e.g., plastics, dyes, though scalability remains a hurdle. This chapter highlights biology's role in transforming waste treatment from recovering resources to degrading persistent pollutants, ushering in low-carbon, circular solutions. Let me know if you'd like to explore genetic engineering advancements or sector-specific applications, e.g., pharmaceuticals, further. Part 4, Advanced Treatment Technologies. 11. Emerging Remediation Technologies. 11.1 Nanomaterials for Heavy Metal Sequestration. Overview: nanomaterials leverage their high surface area and reactivity to adsorb or immobilize heavy metals, e.g., Pb, Hg, Cd, in contaminated soil and water. Key technologies: carbon-based nanomaterials, graphene oxide and carbon nanotubes effectively bind metals via electrostatic interactions. Metal organic frameworks, MOFs, porous structures with tunable sites for selective metal capture, e.g., UIO66 for arsenic removal, iron oxide nanoparticles, magnetite, FeO, nanoparticles enable magnetic recovery post-adsorption. Applications: water treatment, TiO nanocomposites remove 95% of lead from industrial wastewater, MIT, 2023. Soil remediation, nano-zero-valent iron, NZVI, reduces Cr, to less toxic Cr, in contaminated sites. Benefits: high efficiency, 90% metal removal, and reusability. Minimal chemical sludge versus traditional precipitation. Challenges: toxicity risks, Nanoparticle leaching into ecosystems. Scalability, high production costs and complex synthesis. Future prospects, biodegradable cellulose nanocrystals for eco-friendly remediation. 11.2 Electrochemical treatment of leachate overview. Electrochemical methods use electric currents to degrade contaminants in landfill leachate. Key methods: electrocoagulation. Aluminum/iron electrodes generate coagulants to remove organics and heavy metals. Electrooxidation. Boron-doped diamond, BDD. Electrodes produce hydroxyl radicals to break down refractory pollutants, e.g., PFAS. Applications: full-scale plant in Finland achieves 85% cod removal using BDD electrodes. Pilot projects: electrophenton systems treat pharmaceutical leachate with 90% efficiency. Benefits: chemical-free operation and modular design. Effective for complex, non-biodegradable contaminants. Challenges: energy demand, high electricity consumption, 15 kWh/m superscript 3. Electrode fouling, requires frequent maintenance. Innovations: solar-powered electrochemical cells for off-grid applications. 11.3 Robotics in landfill mining and rehabilitation overview. Robotics enhance safety and efficiency in excavating and sorting legacy waste. Key technologies: autonomous excavators. AI-guided machinery identifies and retrieves recyclables, e.g., metals, plastics. Drones with LiDAR, map landfill topography and methane hotspots. Sorting robots, use hyperspectral imaging to distinguish materials, e.g., Zen Robotics Recycler. Applications: Belgium's Remo landfill project, robots recover 60% of materials for recycling. Japan's smart landfills, drones monitor structural stability in real time. Benefits: reduces human exposure to hazardous waste. Recovers valuable resources, e.g., 1 ton of landfill mined plastic saves $200 versus virgin production. Challenges: technical complexity, handling heterogeneous waste streams. High initial costs, $500K $2M for robotic systems. Future trends: swarm robotics for collaborative sorting and excavation. Key takeaways for Chapter 11. Nanomaterials offer precision in metal sequestration but require ecotoxicity assessments. Electrochemical systems bridge gaps in leachate treatment but need renewable energy integration. Robotics revolutionize landfill mining, though ROI depends on material recovery rates. These technologies underscore the shift toward smart, sustainable remediation, aligning with circular economy goals. Policymakers should prioritize funding for pilot projects and address regulatory barriers to adoption. Suggested visuals: schematic of MOF structure capturing heavy metals. Flowchart of electrochemical leachate treatment. Infographic on robotic landfill mining workflow. This chapter positions emerging technologies as critical tools for mitigating legacy pollution and advancing resource recovery. Part B: Smart Systems and Digital Innovations 12. IoT and Smart Waste Management. 12.1 Sensor Networks for Bin Monitoring and Route Optimization Overview. IoT-enabled sensors in waste bins collect real-time data on fill levels, temperature, and location, enabling dynamic collection schedules. Key technologies: ultrasonic sensors, measure bin fill levels, e.g., Enovos Waste Solutions. GPS tracking, monitors collection truck routes via platforms like Big Belly. LoRaWAN connectivity, low power, long-range data transmission for remote bins. Benefits: cost savings. Rotterdam reduced collection costs by 25% using sensor data to optimize routes. Emission reduction, smart routing cuts fuel use by 15-20%, waste advantage, 2023. Public hygiene, alerts prevent overflow in high-traffic areas. Case study: Barcelona's Smart City Initiative, IoT bins reduced pickups by 30%, saving €3.5 million annually. Challenges: Sensor durability in harsh environments, e.g., moisture, vandalism. Data privacy concerns with GPS tracking. Future trends, integration with autonomous electric waste vehicles. 12.2 Predictive analytics for waste collection overview. Machine learning models forecast waste generation patterns using historical data, weather, and socio-economic factors. Key tools, time series forecasting. ARIMA and LSTM models predict daily waste volumes. AI platforms, IBM's Watson and Waste Hero optimize collection frequency. GIS mapping, identifies hotspots for seasonal waste surges, e.g., festivals. Applications, Sol's AI bins, predictive analytics cut collection frequency by 40% in commercial districts. Coventry's smart bins, adjust schedules during holidays using weather and event data. Benefits, reduced operational costs and carbon footprint. Minimized bin overflow and littering. Challenges, requires high quality, granular data. Model accuracy drops during unforeseen events, e.g., pandemics. Innovations, federated learning for privacy-preserving cross-city data sharing. 12.3 Blockchain for transparent waste tracking overview. Blockchain creates immutable records of waste transactions, enhancing accountability in recycling and disposal. Key use cases, plastic credit systems, plastic bank tokens track ocean-bound plastic recovery. EPR compliance, smart contracts automate producer responsibility reporting, e.g., VE chain. Circular supply chains, trace recycled materials from bin to product, e.g., CIRC for EV batteries. Benefits, fraud prevention, tamper-proof records reduce illegal dumping. Stakeholder trust, consumers verify sustainability claims, e.g., digital product passports. Case study, Dubai's blockchain strategy, tracks 100% of construction waste, achieving 95% landfill diversion. Challenges, scalability limits, e.g., Ethereum's 30 transactions/second. Energy-intensive consensus mechanisms, e.g., proof of work. Future trends, green blockchain protocols, e.g., Algorand's pure proof of stake. Key takeaways for Chapter 12, IoT sensors and predictive analytics transform waste collection from reactive to proactive, slashing costs and emissions. Blockchain ensures transparency in circular supply chains but requires energy-efficient upgrades. Integration of AI and IoT enables cities to meet SDG 11, Sustainable Cities, and 12, Responsible Consumption. This chapter underscores how digital innovations are redefining waste management, turning data into actionable insights and fostering accountability across the value chain. Let me know if you'd like to explore specific platforms, e.g., SAP's intelligent waste management, or ethical considerations, e.g., AI bias, further. Suggested visuals, dashboard of real-time bin status and truck routes. Flowchart of blockchain-based EPR compliance. Predictive model accuracy graphs, MAPE scores. Part B, Smart Systems and Digital Innovations 13. AI and Machine Learning Applications 13.1 Waste Generation Forecasting Models Overview. AI models predict waste volumes and composition using historical data, socio-economic indicators, and external variables, e.g., weather, holidays. Key algorithms, long short-term memory, LSTM, networks, capture temporal patterns in daily waste streams, e.g., post-holiday surges. Random forests, handle nonlinear relationships for mixed waste predictions. SARIMA, seasonal ARIMA models cyclical trends in agricultural or tourism-driven waste. Applications, municipal planning. Sol's AI system reduced collection costs by 20% by forecasting peak waste days in commercial districts. Industrial waste, predictive models optimize manufacturing scrap recycling, e.g., Toyota's lean waste management. Benefits, reduces overcapacity in landfills by aligning disposal with predicted volumes. Enables dynamic pricing models for pay-as-you-throw (PAYT) systems. Challenges: data gaps in informal settlements or rural areas. Model drift during disruptions, e.g., pandemics, natural disasters. Future trends: federated learning, collaborative models trained across cities without sharing raw data. Satellite imagery integration: AI analyzes landfill growth via satellite data, e.g., orbital insight. 13.2 Autonomous sorting robots overview: robots equipped with AI vision and grippers autonomously sort recyclables from mixed waste streams. Key technologies: computer vision, cameras and deep learning, e.g., ResNet, YOLO, identify material types, colors, and shapes. Tactile sensors, adjust grip strength for fragile items, e.g., glass. Multi-robot coordination, swarm systems share data to optimize sorting workflows. Case studies: AMP Cortex trademark, sorts 80+ material types at 160 picks/minute, achieving 99% purity in recycling streams. Zen Robotics, Finland heavy picker robots recover construction waste with 95% accuracy, diverting 75% from landfills. Benefits: labor savings, reduces reliance on manual sorters in hazardous environments. Contamination reduction, cuts recycling rejection rates by 30–50%, Waste Dive, 2023. Challenges: high upfront costs, $200K $500K per robot. Struggles with degraded or novel materials, e.g., black plastics. Innovations: self-learning systems, robots improve accuracy via continuous feedback, e.g., Google's RT2. Collaborative robots, cobots work alongside humans in hybrid sorting lines. 13.3 Digital twins for landfill management overview: digital twins create virtual replicas of landfills, simulating physical processes, e.g., decomposition, gas migration, in real time. Key components: IoT sensors, monitor methane levels, temperature, and settlement rates. Simulation software, tools like ANSI or COMSOL model gas diffusion and leachate flow. Machine learning, predicts landfill capacity and stabilizes slopes to prevent collapses. Applications: methane capture optimization, Veolia's digital twin increased gas recovery by 25% at a UK landfill. Risk mitigation, simulates leachate breaches to guide liner repairs. Benefits: extends landfill lifespan by optimizing waste compaction and decomposition. Reduces GHG emissions via proactive gas management. Challenges: complex calibration of multiphysics models. High computational power requirements. Future trends: AI-driven predictive maintenance, alerts operators to equipment failures, e.g., pump breakdowns. Integration with smart grids, directs landfill gas to energy markets during peak demand. Key takeaways for Chapter 13: AI forecasting transforms waste logistics, but requires robust data governance to address equity gaps. Autonomous robots revolutionize recycling economics, though ROI hinges on material purity and labor costs. Digital twins turn landfills into data-driven assets, balancing operational efficiency with environmental compliance. This chapter illustrates how AI and ML are not just tools but paradigm shifts in waste management, enabling smarter cities, safer workplaces, and scalable circular economies. For policymakers, investing in digital literacy and infrastructure is critical to harnessing these technologies equitably. Cross-references: IoT sensors, CH 12.1, for real-time data feeding AI models. Circular economy frameworks, CH 8, for closed-loop systems enabled by robotic sorting. Suggested visuals: neural network architecture for waste forecasting. Video demo of robotic sorting arms in action. 3D rendering of a landfill digital twin with methane hotspots. This chapter positions AI and ML as indispensable allies in achieving zero waste goals, bridging innovation with sustainability. Let me know if you'd like to explore ethical considerations, e.g., AI bias in low-income regions, or sector-specific use cases, e.g., healthcare waste, further. Part 6, Socio-economic and Governance Strategies 14. Community Engagement and Equity 14.1 Grassroots Movements and Citizen Participation Overview. Grassroots movements empower communities to address waste challenges through local action, advocacy, and education, bridging gaps left by institutional failures. Key strategies: Zero Waste Initiatives. Kamikatsu, Japan. A citizen-led movement achieved 80% recycling rates through strict household sorting and community composting. Philippines Mother Earth Foundation trained 1.2 million residents in waste segregation, diverting 40% of Metro Manila's waste from landfills. Citizen Science, Plastic Tide Trackers. Communities map plastic pollution using apps like Literati to pressure policymakers. Community composting hubs. Urban gardens in Detroit and Nairobi convert organic waste into fertilizer via participatory programs. Impact, policy influence. Barcelona's Zero Waste Alliance pushed for a citywide ban on single-use plastics in 2021. Behavioral shifts. Brazil's Pimp My Caroca campaign reduced stigma against informal waste pickers through art and activism. Challenges: burnout. Volunteer-driven efforts struggle with sustainability. Scalability. Local successes rarely translate to national policies without institutional support. Tools for empowerment. Participatory budgeting for waste infrastructure, e.g., Porto Alegre, Brazil. Social media campaigns, e.g., Number Break Free from Plastic. 14.2 Inclusive Waste Management for Informal Sectors Overview. The informal sector, 15-20 million waste pickers globally, plays a vital role in recycling but faces systemic exclusion and hazards. Key issues: health risks, exposure to toxins, injuries, and respiratory diseases, e.g., Delhi's waste pickers have a life expectancy 20 years below average. Economic marginalization, earn $2/day with no social security or legal recognition. Inclusive models, integration into formal systems. Brazil's catador cooperatives, legally recognized waste picker cooperatives, manage municipal recycling, achieving 90% material recovery in Belo Horizonte. India's Safecina, a collective of 18,000 workers, partners with corporations for e-waste recycling. Fair trade certification, Plastic for Change, ensures fair wages for informal workers in India's plastic supply chains. Policy innovations, extended producer responsibility, EPR, credits, allocate a percentage of EPR fees to informal workers, e.g., South Africa's PROS. Health and safety programs. Colombia's Recuperar provides PPE and medical checkups for 12,000 waste pickers. Challenges: resistance from formal waste management companies. Lack of data to quantify informal sector contributions. Case study: Egypt's Zabalayan, a Coptic Christian community, recycles 85% of Cairo's waste but faces displacement due to privatization. 14.3 Addressing environmental justice in waste disposal overview. Marginalized communities, often low-income, indigenous, or people of color, disproportionately bear the brunt of landfills, incinerators, and illegal dumping. Key issues: proximity hazards. Warren County, USA, a 1982 PCB landfill in a predominantly black community sparked the environmental justice movement. Agbogbloshie, Ghana, a e-waste dump site exposes 250,000 residents to lead, cadmium, and dioxins. Policy neglect. Sacrifice zones. Regions like Louisiana's Cancer Alley host 150+ petrochemical plants near black communities. Strategies for equity. Legal advocacy. U.S. Executive Order 12898, 1994 mandates federal agencies to address environmental racism. UN Special Rapporteur on Toxics investigates human rights violations linked to waste dumping. Community-led solutions. Cherokee Nation's landfill resistance. blocked hazardous waste imports through tribal sovereignty claims. Environmental Justice Atlas, a global database of 3,800 plus conflicts used to lobby policymakers. Tools for accountability, health impact assessments, HIA's mandate evaluations of waste facilities on vulnerable populations. Community benefit agreements, BAs ensure waste projects fund local schools or clinics, e.g., Los Angeles Sun Valley Park deal. Challenges, corporate greenwashing, false claims of green incinerators in marginalized areas. Data gaps, lack of race/class disaggregated waste data in many countries. Key takeaways for Chapter 14, grassroots movements prove that local action can drive systemic change but require institutional partnerships for scale. Informal sector inclusion is not just ethical but practical. Integrating waste pickers boosts recycling rates and reduces costs. Environmental justice demands dismantling systemic inequities through policy, litigation, and centering marginalized voices. This chapter underscores that equitable waste management is inseparable from social justice. Without addressing power imbalances and historical inequities, technical solutions alone will fail. Cross-references, Circular Economy Frameworks, CH8, for Inclusive Business Models. Policy and Regulatory Landscape, CH3, for Global Equity Gaps. Suggested visuals, infographic, Global Map of Environmental Justice Conflicts. Case Study Spotlight, Brazil's Catador Cooperatives. Timeline, Key Milestones in the Environmental Justice Movement. Discussion questions. 1. How can cities balance privatization with protecting informal workers' livelihoods? 2. What role should reparations play in addressing historical waste injustices? This chapter challenges readers to view waste not just as an environmental issue but as a reflection of societal values and to act accordingly. Let me know if you'd like to explore reparative economics or decolonial approaches further. Part 6, Socio-economic and Governance Strategies. 15. Economic Models and Financing. 15.1 Carbon Credits and Green Bonds. Carbon credits, mechanism. Carbon credits permit companies to emit a set amount of CO, with excess credits tradable on markets like the EU Emissions Trading System, ETS. Projects such as landfill gas capture or waste-to-energy plants generate credits by reducing emissions. Verification, standards like the Verified Carbon Standard, VCS, ensure legitimacy, requiring third-party audits, e.g., Gold Standard certified composting projects in Kenya. Case study, Delhi's Gazipur landfill captures methane to earn carbon credits, funding remediation while cutting 2.7 million cubic meters of CH daily. Green bonds, purpose, finance eco-friendly infrastructure, e.g., recycling facilities, anaerobic digesters. Examples, Apple's $2.2 billion green bond, 2023 funds clean energy and circular supply chains, including iPhone material recovery. World Bank's waste management bonds, support municipal composting in Colombia and India. Challenges, greenwashing risks, rigorous reporting frameworks, e.g., ICMA's green bond principles, are critical. 15.2 Cost-effective public-private partnerships, PPPs, key features, risk sharing, private firms manage operations, while governments provide oversight, e.g., Singapore's Semeco landfill, managed by Semcorp. Performance-based contracts, payments tied to waste diversion targets, e.g., Lagos, Nigeria, achieving 40% recycling via PPPs. Examples, Copenhagen's Amager-Baki WTE plant, a PPP incinerator doubles as a ski slope, powering 150,000 homes. India's Swachh Bharat mission, private firms handle 60% of urban waste collection under municipal contracts. Challenges, accountability, ensure transparency via open data platforms, e.g., open contracting. Equity, include informal workers in contracts, e.g., Brazil's Catador cooperatives in São Paulo's PPPs. 15.3 Circular Economy Business Models. Key models, Product as a Service, PaaS, Philips Light as a Service, leases lighting systems, reclaiming 90% of materials for reuse. Mud Jeans, rents denim, recycling old pairs into new garments. Take Back Programs, Dell's closed-loop recycling, recovers 100 m&pounds of e-waste annually for new products. IKEA's buyback scheme, resells used furniture, diverting 46 items from landfills, 2023. Profitability drivers, resource efficiency, interfaces carpet recycling cuts material costs by 30%. Consumer demand, 73% of global consumers pay premiums for sustainable brands, Nielsen, 2023. Challenges, upfront costs, H&M's garment recycling initiative faces high sorting expenses. Behavioral shifts, TerraCycle's loop requires retailers to redesign packaging for reuse. Key takeaways for Chapter 15, Carbon credits and green bonds bridge funding gaps but demand rigorous oversight to prevent greenwashing. PPPs optimize efficiency but must prioritize equity through inclusive contracting and worker protections. Circular models prove profitability and sustainability can coexist, though scalability hinges on policy support, e.g., EPR laws and consumer buy-in. Policy recommendations, mandate ESG disclosures for green bond issuers. Offer tax incentives for circular businesses, e.g., France's anti-waste law. Integrate informal sectors into PPP frameworks via cooperative partnerships. Case Study Spotlight, Amsterdam's Circular Funding Program, combines green bonds and PPPs to finance zero-waste startups, creating 1,200 plus jobs. Future trends, blockchain-enabled carbon credit trading, e.g., Climate e-trade. Outcome-based financing, investors fund waste projects in exchange for a share of carbon revenue. This chapter underscores that financial innovation is the linchpin of sustainable waste systems balancing profit, planet, and people. Let me know if you'd like to explore blended finance mechanisms or sector-specific models, e.g., construction waste, further. Part 6, Socio-economic and Governance Strategies 16. Global Case Studies 16.10 Waste Cities, San Francisco, Kamikatsu, Ljubljana San Francisco, USA, Key Initiatives, Mandatory Recycling/Composting Laws, enforced since 2009, requiring residents and businesses to separate waste into recyclables, compostables, and landfill-bound items. Pay-as-you-throw, PAYT fees based on landfill bin size incentivize waste reduction. Partnerships, collaboration with Recology for citywide collection and education. Outcomes, 80% diversion rate, 2023, aiming for zero waste by 2030. Compost used for local vineyards and farms. Challenges, high costs for contamination monitoring. Persistent issues with multifamily housing compliance. Kamikatsu, Japan, Key Initiatives, 45 waste categories, residents sort waste into 45 plus types for reuse, recycling, or composting. Zero Waste Academy, community education and a circular shop for exchanging used items. Outcomes, 80% recycling rate, with only 20% incinerated, no landfill since 2020. National Model for Rural Waste Management. Challenges, labor-intensive sorting for aging population. Limited scalability to urban areas. Ljubljana, Slovenia, Key Initiatives, first EU capital with zero waste strategy, closed-loop systems for organic waste, composting biogas, and construction materials. Door-to-door collection, weekly pickups for 70% of households. Outcomes, 68% diversion rate, 2023, reduced landfill use by 90% since 2008. Awarded European Green Capital, 2016. Challenges, balancing tourism-driven waste surges. Funding high-tech infrastructure. Lessons learned, policy plus community engagement equals success. San Francisco's mandates and Kamikatsu's grassroots rigor show complementary approaches. Local context matters, urban versus rural strategies require tailored solutions. 16.2 E-waste management in the EU and Ghana. European Union, key initiatives, WEEE Directive, mandates 65% e-waste collection and 85% recycling by 2025. Circular Electronics Partnership, brands like Philips and Dell design for recyclability. Outcomes, 55% e-waste recycled, 2023, with Belgium and Netherlands leading at 75%. Rare earth recovery from old electronics, e.g., Bamako smelters. Challenges, consumer hoarding of devices. Illegal exports to developing nations. Ghana, Agbogbloshie, key issues, informal recycling, 40,000 plus workers burn e-waste for metals, exposing communities to lead and dioxins. Health impacts, life expectancy here is 10-20 years below national average. Innovations, Fairphone's ethical sourcing, partners with local recyclers for safer practices. UN STEP initiative, provides protective gear and training for workers. Challenges, lack of formal infrastructure. Global e-waste dumping perpetuating harm. Lessons learned, regulation plus tech equals progress. EU's WEEE contrasts with Ghana's need for investment and justice. Global responsibility, curbing illegal exports is critical to equitable solutions. 16.3 Innovations from emerging economies, India, Brazil, Rwanda. India, key innovations, Swak Bharat mission, national campaign improving urban sanitation and waste segregation. Waste to wealth startups, Kabetawala, online scrap marketplace, and TrashCon, AI sorting robots. Outcomes, 30% reduction in open dumping, 2014-2023. Delhi's landfill biomining projects reclaiming land. Brazil, key innovations, Catadores cooperatives, 800 plus cooperatives integrate informal waste pickers into formal systems, e.g., Belo Horizonte's 90% recycling rate. Reverse logistics laws, EPR for packaging, electronics, and batteries. Challenges, corporate resistance to EPR costs. Urban sprawl complicating collection. Rwanda, key innovations, plastic bag ban, 2008 first African nation to enact, reducing litter and protecting agriculture. Kigali's waste-to-energy plant, processes 50 tons/day, powering 1,000 homes. Outcomes, cleanest city in Africa, Unhabitat, 2023. 60% waste diverted from landfills. Lessons learned, informal sector integration, Brazil's cooperatives and India's startups show economic and environmental wins. Bold policies work, Rwanda's plastic ban proves strict laws can drive cultural shifts. Chapter takeaways, zero waste cities thrive through policy rigor, tech, and community buy-in. E-waste management demands global equity. Rich nations must curb dumping, while poorer ones need investment. Emerging economies innovate despite resource constraints, offering scalable models for grassroots circularity. Cross-references, Circular Economy Frameworks, CH8, for EU's WEEE and Brazil's EPR. Community Engagement, CH14, for Kamikatsu's and Kigali's grassroots efforts. Discussion questions, 1. How can Global North cities learn from Global South innovations? 2. What ethical obligations do tech companies have in e-waste hotspots like Agbogbloshie? This chapter illustrates that sustainability is achievable across diverse contexts when innovation meets equity. Let me know if you'd like to explore specific metrics, e.g., CO savings, or cultural narratives, e.g., Rwanda's Umuganda community cleanups, further. Part 7, Future Challenges and Opportunities. 17. Tackling Emerging Waste Streams. 17.1 Managing Solar Panel and Wind Turbine Waste Overview. The renewable energy transition is generating a new wave of waste. Solar panels contain toxic materials, e.g., lead, cadmium, and non-recyclable polymers. By 2050, global solar waste could reach 78 million metric tons, IRENA. Wind turbines, fiberglass blades, up to 100 m long, are landfill-bound due to complex composite materials. Over 43,000 blades will be decommissioned by 2030, Global Wind Energy Council. Current challenges: recycling gaps. Only 10% of solar panels are recycled in the US, most are crushed and landfilled. Logistical hurdles: transporting massive turbine blades to limited processing facilities. Innovations: solar, EU Circusol project, pilots circular leasing models for panels, ensuring manufacturer take-back. Silicon recovery: companies like Rossi extract high-purity silicon for reuse. Wind, blade recycling: Siemens Games's recyclable blade registered trademark, and Veolia cement CO processing, blades as raw material. Policy needs: extended producer responsibility, EPR mandate recycling targets for manufacturers. Standardized design, modular panels and blades for easier disassembly. 17.2 COVID-19 PPE and medical waste surges overview. The pandemic triggered a tenfold increase in medical waste. Scale: WHO estimates 89 million masks and 140 million test kits used monthly at the pandemic's peak. Environmental impact: 1.6 million tons/day of COVID-related plastic waste entered oceans in 2020, PNAS. Challenges: contamination risks: infectious waste burned openly in low-income nations, releasing dioxins. Material complexity: multi-layer masks and rapid antigen tests resist recycling. Solutions: biodegradable PPE, mushroom-based masks, myco-masks, and starch-based gloves. Autoclave shredding: South Korea's three-step sterilization for safe recycling of PPE into pellets. Public awareness: Vietnam's Green Mask campaign promotes reusable alternatives. Case study: India's COVID waste crisis. 2021 peak saw 56,000 tons/month of medical waste, overwhelming incinerators. Startups like Vartan Recycling repurposed PPE into construction materials. 17.3 Space debris and orbital waste management overview. Over 36,000 tracked objects, defunct satellites, rocket parts, orbit Earth, threatening collisions, and the Kessler syndrome, cascading debris fields. Risks: satellite collisions: a single crash can generate thousands of fragments, e.g., 2009 Iridium Cosmos collision. Costs: debris avoidance maneuvers cost satellite operators $10M $20M annually, ESA. Innovations: active debris removal, ADR, ESA's ClearSpace 1, first mission, 2026, to capture a 112 kg defunct satellite. Astroscales LCD, magnetic docking for debris retrieval. Sustainable design: NASA's Orca, on-orbit recycling of old satellites into new parts. Biodegradable satellites: Kyoto University's wooden satellites, 2024 launch. Policy gaps: lack of binding treaties, current guidelines, e.g., UN's 25-year deorbit rule, are voluntary. Funding: ADR missions cost $100M plus, shared financing models are critical. Key takeaways for Chapter 17, 1. Renewable energy waste demands urgent R&D and EPR laws to avoid trading fossil fuel harms for new pollution. 2. Pandemic waste exposed systemic fragility, future health crises need circular PPE systems. 3. Space debris requires global governance akin to climate agreements to preserve orbital sustainability. Policy recommendations: solar/wind, tax incentives for recyclers and R&D grants for material innovation. Medical waste: integrate PPE into circular economy frameworks, e.g., EU Single-Use Plastics Directive. Space: levy orbital parking fees to fund debris removal and enforce abiding mandates. Future outlook: emerging waste streams test humanity's capacity for foresight. By embedding circularity into renewable tech, healthcare, and space exploration, we can transform these challenges into catalysts for systemic innovation. Cross-references, e-waste management, ch 16.2, for parallels in toxic material recovery. Circular economy models, ch 8, for scalable solutions. Discussion questions. 1. Should renewable energy subsidies require recycling plans for end-of-life equipment? 2. How can spacefaring nations equitably manage orbital commons? This chapter underscores that tomorrow's waste crises are born from today's solutions, urging proactive, collaborative action to stay ahead of the curve. Part 7, Future Challenges and Opportunities. 18. Climate Change and Waste Resilience. 18.1 Waste Sector Contributions to GHG Mitigation. Overview. The waste sector contributes 5% of global GHG emissions, primarily methane, CH, from landfills and CO from incineration. Methane, 36 times more potent than CO over 100 years, makes landfills a critical target for mitigation. Key strategies: landfill gas capture. Example, U.S. Landfill Methane Outreach Program, LMOP, reduced emissions by 100 mCOE since 1994. Technology: gas-to-energy systems power 1.5 million U.S. homes annually. Waste-to-energy, WTE, case study, Sweden incinerates 50% of its waste, supplying 8% of district heating and reducing fossil fuel reliance. Recycling and composting, impact, San Francisco's 80% diversion rate avoids 1.2 mCOE/year. Organic waste, composting cuts methane by diverting food scraps, e.g., South Korea's 95% food waste recycling rate. Policy tools, carbon pricing, EU emissions trading system, ETS, incentivizes WTE efficiency. Extended producer responsibility, EPR mandates for electronics and packaging, e.g., EU's circular economy package. Challenges, funding gaps, low-income nations lack infrastructure for gas capture. Behavioral barriers, public resistance to composting or source separation. Innovations, biocar production, converts organic waste into stable carbon for soil sequestration. Methanotrophs, engineered bacteria to oxidize methane in landfills. 18.2 Adaptive strategies for extreme weather events. Risks to waste systems, infrastructure damage, floods breach landfills, e.g., Hurricane Katrina's 2 m tons of debris. Service disruption, typhoons halt collections, e.g., Philippines 2020 Goni typhoon stranded 10k tons of waste. Hazardous spills, storm surges spread medical or chemical waste, e.g., 2017 Houston floods. Adaptive measures, resilient infrastructure, floodproof landfills, Japan's elevated landfills with impermeable liners. Modular facilities, mobile waste units deployed post-disaster, e.g., Puerto Rico post-Maria. Emergency protocols, pre-positioned resources, FEMA's debris management plans for rapid response. Decentralized systems, community composting hubs reduce reliance on centralized plants. Technological solutions, IoT monitoring, real-time sensors track landfill stability and methane leaks during storms. Predictive analytics, AI models forecast flood impacts on waste flows, e.g., Rotterdam's climate adaptation strategy. Community engagement, education, Philippines Eco Waste Coalition trains communities in disaster waste segregation. Citizen science, apps like Trozhout map illegal dumps post-disaster. Challenges, cost, retrofitting landfills costs $10m $50m. Coordination, fragmented agency roles delay responses, e.g., 2011 Thailand floods. Case studies, New Orleans post-Katrina, debris recycling generated 1.5 m tons of reusable material. Netherlands sand motors, nature-based solutions protect coastal waste facilities from sea level rise. Key takeaways for Chapter 18, mitigation and adaptation are interlinked, reducing landfill methane, mitigation, also minimizes fire risks during droughts, adaptation. Equity matters, low-income coastal zones face dual threats of climate impacts and waste pollution. Policy synergy, integrate waste resilience into national climate action plans, e.g., NDCs under the Paris Agreement. Cross-references, smart systems, CH12, for IoT applications in disaster response. Circular economy, CH8, for reducing waste generation preemptively. Discussion questions: 1. How can climate financing mechanisms, e.g., Green Climate Fund, prioritize waste resilience? 2. Should methane mitigation from landfills be mandatory under global climate treaties? This chapter underscores that climate-resilient waste systems are not optional but essential for safeguarding ecosystems and public health in a warming world. Chapter 19, Vision 2050, Pathways to Zero Waste. 19.1 Policy Roadmaps and Global Collaboration Framework for Action. Global agreements strengthen international frameworks like the Basel Convention and Paris Agreement to include explicit waste reduction targets. The EU's Circular Economy Action Plan, 2030 recycling targets, 60% municipal, 70% packaging, serves as a model for binding regional policies. National policies implement extended producer responsibility, EPR, laws globally, mandating companies to manage product life cycles. Examples include South Korea's volume-based waste fee system and Rwanda's plastic ban. Cross-border collaboration, establish funding mechanisms, e.g., Green Climate Fund allocations, for technology transfer to low-income nations. The Global Alliance on Circular Economy and Resource Efficiency, GACERA, exemplifies multilateral cooperation. Challenges: political fragmentation, enforcement gaps, and balancing economic growth with sustainability. 19.2 Disruptive technologies on the horizon. Innovations driving change, advanced recycling, chemical recycling, e.g., Carbio's enzymatic PET breakdown, and gasification for non-recyclables. AI-powered sorting robots, AMP robotics, achieve 99% purity in material recovery. Waste prevention, edible packaging, not seaweed-based materials, and blockchain traceability, IBM's plastic bank, to ensure supply chain transparency. Energy recovery, plasma gasification and microbial fuel cells converting organic waste to energy. Considerations: scalability, e.g., modular systems for rural areas, ethical AI use, and job transition programs for displaced workers. 19.3 Educating future generations for sustainability. Building a zero-waste mindset, formal education, integrate sustainability into curricula, e.g., Finland's interdisciplinary climate modules. Universities like Stanford offer degrees in sustainable resource management. Vocational training, green job initiatives, e.g., India's Skill Council for Green Jobs, to equip workers for roles in recycling, renewable energy, and eco-design. Public engagement, gamified apps, Olio for food sharing, and VR experiences, UN's Clean Seas campaign, to foster behavioral change. Challenges: bridging the digital divide, updating curricula dynamically, and combating misinformation. Conclusion: synergy for systemic change. Achieving zero waste by 2050 demands interconnected efforts. Policy and tech, global treaties incentivize R&D, while EPR laws ensure corporate accountability. Education and innovation, skilled workforces drive tech adoption, supported by lifelong learning platforms. Equity and collaboration, address disparities through funding and inclusive design, e.g., India's informal sector integration. Call to action: governments, ratify a global plastics treaty by 2025. Corporations, invest in circular design and transparency. Individuals, advocate for local zero waste initiatives. Inspiring case studies: Kamikatsu, Japan, 80% recycling via hyper-local sorting. San Francisco, 80% diversion through mandates and partnerships. Final note, the path to 2050 is paved with innovation, collaboration, and education. By learning from global successes and scaling solutions urgently, a zero-waste future is within reach. Appendices: a glossary of key terms. Anaerobic digestion, a biological process breaking down organic waste in oxygen-free environments, producing biogas and digestate. Circular economy, an economic system aimed at eliminating waste through continual resource reuse, recycling, and regeneration. EPR, extended producer responsibility policy requiring producers to manage the disposal/recycling of their products post-consumer use. Leachate, contaminated liquid formed by water percolating through waste, often containing toxins. WTE, waste-to-energy conversion of non-recyclable waste into heat, electricity, or fuel. Urban mining, extraction of valuable materials, e.g., metals, from waste streams like e-waste. B. Global waste management standards and metrics, ISO standards, ISO 14001, environmental management systems. ISO 15270, guidelines for plastic waste recycling. International agreements, Basel Convention, regulates transboundary movement of hazardous waste. UN Sustainable Development Goals, SDG 12 targets sustainable consumption and waste reduction. Metrics, diversion rate, percentage of waste redirected from landfills via recycling/composting. Carbon footprint, GHG emissions measured in CO equivalents, e.g., methane from landfills. See software tools for waste analytics. WasteWorks, a GIS-based platform for optimizing waste collection routes and landfill siting, commercial. CIMAPro, lifecycle assessment, LCA, software for evaluating environmental impacts of waste systems, subscription-based. OpenLCA, open-source LCA tool for modeling circular economy scenarios. IBM Tririga, AI-driven waste tracking and analytics for enterprises. References, APA style, academic papers, Ghosh, SK, and Deebnath, B. 2021. Sustainable Management of E-Waste in Developing Economies. Journal of Cleaner Production, 294, 126,305. https://doi.org/10.1016/j.jclpro.2021.126305, Kazai, S, ETAL, 2018. What a Waste 2.0, a global snapshot of solid waste management to 2050. World Bank. Industry Reports, Global E-Waste Monitor. 2023, International Telecommunication Union, ITU. https://www.itu.int, Ellen MacArthur Foundation. 2020, Circular Economy Action Plan. European Commission. Policy Documents, United Nations. 2015, Paris Agreement. UNFUC. EPA. 2022, Landfill Methane Outreach Program, LMOP, Guidelines. https://www.epa.gov/lmop, Tools and Software, Pre-Sustainability. 2023, CIMAPro LCA Software. https://cimapro.com, WasteWorks. 2023, User Manual. Geosyntec Consultants. Notes, formatting, references follow APA style, with hyperlinks for digital sources. Accessibility, software tools include licensing type, e.g., open source, commercial. Cross-referencing, glossary terms align with chapters, e.g., EPR in policy roadmaps. This structure ensures clarity and utility, supporting readers in applying the book's advanced concepts while adhering to academic rigor.